The integration of network functions virtualization (NFV) in information-centric networks (ICNs) is a pivotal aspect of next-generation network architectures. Traditional network topologies are facing challenges in managing massive data flow, leading to high energy consumption and costs. NFV allows for the virtualization of network functions, enabling the incorporation of new services and reducing operating expenses. ICNs, on the other hand, focus on the content of the data, rather than the location of the hosts, allowing for better support, load balancing, and management of big volumes of data. ICNs use content addressing tables, temporary storage in routers, and transport layer security (TLS) to guarantee information security. The role of the Content Delivery Network (CDN) is also emphasized, allowing for fast transfer of files and better performance. Virtualization of network functions is discussed, enabling the incorporation of new services and reducing operating expenses. NFV allows for the decoupling of physical devices, enabling them to run logically on standard servers. The use of NFV in ICNs is critical, as it enables the installation of virtual network functions anywhere and without investment in new equipment, optimizing space and reducing power consumption. The article highlights the importance of ICNs in managing the recovery of objects from the data that circulates on the network and guaranteeing information security. The use of NRL is proposed to overcome some of the weaknesses of ICNs. The essential elements of an ICN are illustrated in Figure 2, showcasing the unique identifiers for each object name, named data objects, NDOs, forwarding information, data routing, application programming, and temporary storage of content in routers. In the NFV context, segmentation at the software and hardware level allows for flexibility in decentralizing network functions. Scalability processes increase flexibility in capacities and services in the network structure. Implementation and maintenance services can be carried out more economically and dynamically. Figure 3 highlights the differences between traditional networks and the virtualization of network functions. Compute instances that fulfill specific functions in NFV include virtual machine hypervisors, containers, and virtual machines, VMs. Virtual network functions, VNFs, run within VMs or containers. Segmentation of the network through virtualization techniques provides better support for performance and functionality in network structures. NFV network architectures include 4 types: centralized, decentralized, distributed, and edge network architectures for dynamic virtual networks, DVNA. Centralized network structures are the most used due to their simplicity, with VNFs installed in data centers or cloud service providers' network infrastructures. Decentralized network architectures have VNFs localized in the customer's infrastructure. Distributed network architectures combine centralized and decentralized structures, optimizing growth, integrity, and viability in VNF construction. Edge network architectures integrate cloud computing into the NFV network structure, with virtualization of services offered to users at the edge of the network. Integrating NFVs into information-centric networks, ICNs, involves linking the virtualization layer with ICNs through the contents of routers using the named data object, NDO, equivalent to the virtual functions of NFVs. This integration is depicted in Figure 8. The integration of network function virtualization, NFV, and information-centric networking, ICN, is a promising approach to optimize network performance and provide benefits to users and providers. Figure 8 illustrates the integration of NFVs into ICNs, enabling the collaborative process of integration between both network technologies. However, NFV still faces challenges, including the need for technological maturity, practical implementation, and management of network functions. The virtualization of network functions must ensure an optimal level of service per user, guaranteeing that required functions can be used without inconvenience. Despite the benefits of NFV, it faces challenges related to commercial implementation, including competition with other products, integration issues with current network topologies, and lack of knowledge and standards. To address these challenges, best practices, such as learning and experimenting through training, can be employed. NFVs are more oriented towards remote programming using network resources at the function level, which can activate malicious software. Therefore, security in the field of virtual network functions, VNFs, is not fully developed, and challenges related to improving NFV performance, measurement of network performance, and security of the network must be addressed. The integration of NFV with other next-generation network technologies, such as fat tree or B-cube network architectures, is a potential area of future work. The achievement of agreements in terms of standards makes it possible to address new technical challenges and provide solutions for launching new virtualized services. The transformation of computing at the edge requires significant transformations and efforts by cloud service providers. Through automation, organization, and virtualization, improvements in the operation of NFV can be obtained, transforming current network infrastructures in terms of implementation, operation, and management of large volumes of data. Planning and management of various providers are necessary to seamlessly migrate services from one network infrastructure to another. NFV has gradually become a network technology with a great innovative impact on traditional and next-generation network structures. However, it is still pending to explore all its potential, and challenges or difficulties that it may present to obtain a variety of benefits that this network technology offers. The authors review existing literature on network function virtualization, NFV, and software-defined networking, SDN, highlighting the challenges and best practices for deploying these technologies. They cite various studies, including 28, 29, and 30, which discuss the opportunities and challenges of NFV, as well as the transport network function virtualization. The authors also reference 31, which provides an overview of the challenges and best practices for deploying NFV in SDN. The authors then discuss the management and orchestration challenges in NFV, citing 32, which highlights the need for efficient management and orchestration mechanisms to ensure the smooth operation of virtualized network functions. They also reference 33, which surveys caching mechanisms in information-centric networking, ICN, a key aspect of NFV. The authors then shift their focus to network topologies, citing 34, which compares and contrasts fat tree and B-cube topologies for data center networks. They also reference 35, 36, and 37, which provide an overview of ICN baseline scenarios and research challenges. The author's review of the literature highlights the complexity of NFV and SDN deployment, as well as the need for efficient management and orchestration mechanisms. They also emphasize the importance of ICN in NFV, citing the need for caching mechanisms to ensure efficient data delivery. The author's discussion of network topologies highlights the trade-offs between different topologies, including fat tree and B-cube. They also reference the ICN baseline scenarios and research challenges, emphasizing the need for further research in this area. The literature review provides a comprehensive overview of the challenges and opportunities in NFV and SDN deployment, highlighting the need for efficient management and orchestration mechanisms, as well as the importance of ICN and caching mechanisms. The author's discussion of network topologies provides a nuanced understanding of the trade-offs between different topologies, emphasizing the need for further research in this area.